right. So for this one, we've got a red button is accidentally pushed and it launches an ICBM. The ICBM leaves the sea surface with a speed of 51, I shouldn't have done that, 5,100 meters per second at an angle of 70 degrees. The supervising officer is on a cruiser, 500 kilometers. Behind the sub. She launches a rocket to intercept and destroy the ICBM, and it reaches a height of 1,000 meters. 1,000 kilometers, sorry. So this ICBM is going to be in parabolic motion. Similar to that. And then at 1,000 meters, so when this value is 1,000 kilometers, sorry, then we want our rocket to slam into it. And we need to find the constant acceleration of the rocket such that it will intercept, neglect air friction, and the other thing that's given is that the rocket starts 20 seconds after the ICBM is launched. So we just need to find the time where our ICBM reaches 1,000 kilometers, and then use that time to figure out how much time the rocket has to see the force that we need. So first of all, let's expand our ICBM's equations of motion here. So to start off, we've got 5,100 meters per second at an angle of 70 degrees. I realize that angle is nowhere near 70 degrees. I'm just going to make it slightly better than this. So 70 degrees I think would be more like that. So 5,100 meters per second. There's a slightly more accurate triangle. Okay, and so then this guy here is going to be 5,100 times the cosine of 70 degrees. And this one here is going to be 5,100 meters per second times the sine of 70 degrees. And I'm going to call this my Vy, and I'm going to call this my Vx. Just to save me the sake of writing these out all the time. So the x direction will matter, but for now we're just going to concentrate on the y. So in the y direction, we have Fy equals, so if we look at our ICBM as it flies, we've got an mg force, and that's it. We really just, as it's unpowered after it leaves, then that's all we've got. So it's just minus mg, which equals ma. And so then our acceleration is just minus g. And now we can use our kinematic equations and say that our final y is going to be our initial y plus our initial velocity in the y direction times time plus 1/2 at squared. And we have our initial velocity here, so maybe I'll put a little I on these guys just to Maybe 2, just for the sake of not messing up or not having it be too confusing. I'll use this notation instead, like that. All right, so there's my VYI. My acceleration, my initial y is 0, so I can get rid of that. And in fact, I know what my YF is as well. It's 1,000 kilometers, so I can fill that in. So I've got 1,000 kilometers is equal to my 5,100 meters per second times the sine of 70 degrees times t plus, or not plus because it's a minus g, minus 1/2 of 9.8 meters per second squared t squared. Or I can rearrange this into 0 equals minus 1,000 kilometers. Actually, I might as well put this all into meters. So minus 1,000, and I actually might as well put it minus 1.0 times 10 to the minus 6 meters. Doing that out, that's 4.79243 times 10 to the 3 meters per second t minus 4.9 meters per second squared t squared. So now everything's in meters and seconds, so that's good. I can use the quadratic equation here and say that t is minus 4.79243 times 10 to the 3 meters per second plus or minus square root 79243 minus 4 times 1 times 10 to the 6. That should be a plus 6, my apologies. Meters times minus 4.9. Square root of all over 2 times minus 4.9 meters per second squared. Okay. So then doing out some of this here, so this is 489.023 seconds plus or minus 1835.044, and that would be in meters per second over 2 times 4.9 meters per second squared. So then our t is 301.774 seconds or 676.273 seconds. And these two times would just correspond to 2 points on the parabola where it equals 1,000 kilometers. So this point and this point in my rough drawing here. But we're only interested in the earlier time, so we want to hit it at the earlier time. So we're just going to use this time. Okay, so there's our time. To get the distance now that our rocket has to travel, as our rocket needs to travel a distance of 500 kilometers plus plus our x for ICBM, and then in the y is the 1,000 kilometers. Okay, so there's our ICBM motion there. We need to still solve for our x for our ICBM. So we can use kinematic equations again. So xf is xi plus vxit. And recalling from our triangle above, our vxi is just 5,100 times the cosine of 70. And our xi is just going to be 0. So it's just 5,100 meters per second times the cosine of 70 degrees times our time. And so this comes out to be, where was I here? 1744. 0.30 meters per second times our time, which is 301.774 seconds, which comes out to 526,385.212 meters. So it turns out I've drawn this a little bit extended because it's about 500 kilometers, so it's pretty much the same distance either way. So now we have our full rocket flight. Now the thing to remember is that we're told the rocket starts 20 seconds after the launch of the ICBM. So that means that the time our rocket has is the rocket time, 301.774 seconds, minus 20 seconds. So the flight needs to take 20 seconds less time because it starts 20 seconds later. And so that makes it 281. So that's our time for a rocket. The rocket is going to travel in a straight line. And we just need to find the constant acceleration of the rocket. It doesn't matter what force is being applied, we just need to know what acceleration the rocket needs. And so for that we can use our kinematic equations. And so we're just going to use an RF version. So RF is Ri plus V naught T plus 1/2 a T squared. And we're assuming the rocket starts from rest, so that's 0. We're starting at 0, so that's 0. So luckily we just need to know our distance, and we can solve for our acceleration using our time. Now our distance is, this is our r here. And so from Pythagorean theorem, just filling in a couple of things here. So we've got 500 kilometers. We've got our ICBM distance, which is this 526.385 kilometers. And then this is 1,000 kilometers. So then our r is here. So our r squared is 500 kilometers plus 526.385 kilometers plus 1,000, and that should be squared, plus 1,000 kilometers squared. So our r is 1432.992 kilometers, which put it into meters is 1.432992 times 10 to the 6 meters. Okay, and so we have from our kinematic equation 1.432 992 times 10 to the 6 meters is 1/2 AT squared. We know our time and we're solving for our acceleration, so it's 2 times this value. Over our time, which we solved as 281.774 seconds, and that should be squared. And this comes out to be 36.097 meters per second squared. And so then there's our acceleration of a rocket that we need to collide with the ICBM in time. Okay, so checking through the solution. So we need to find our time. It comes out to be 301.8 seconds, so that looks good. So we need to find the horizontal range, which comes out to be 526, so that looks good. Just some rounding differences there. For the rocket, it needs to be 20 seconds less, so 281.8. The total distance traveled is going to be the sum. Our initial velocity is 0. So then our acceleration comes out to be 36.1 meters per second squared. So that looks good.